We begin with a polytope, a green face, purple face. We fold out the purple face, we put it over here. We take the green face, we put it over here. We label the vertices of the green face, and it took us quite a while to get to where we could do that, but here they are. Having labeled the vertices, we ask, what's the slope of this triangle up here? In other words, what's the slope of this line segment in the XZ, in a plane parallel to the YZ plane? Okay, so we ask, what's the rise, what's the run, what's the slope? The rise is a change in Z. Z goes this way, and Z goes from f of xy to f of xy plus delta y. So the change is f of xy plus delta y minus f of xy. Here it is. The run is from here to here. These lines are perpendicular to both of these sides, so this is a rectangle, so this is equal to this, and delta y goes in this direction, so the run is delta y. So that the slope is f of xy plus delta y minus f of xy divided by delta y. Over here, we do the same thing. We label the four corners of this purple polytope. We get the labeling here. Again, this went a little better than that one, quite a bit better. Some people still had a little bit of trouble, but we got the labels. And we write the slope. Okay, the z coordinate goes from f of x plus delta xy to f of xy. Here it is, or here it is. Okay, here they are, and here they are. So that's going to be this minus this, f of xy. The rise is going to be f of xy minus f of x plus delta xy. Now that's in the opposite order to what we had before. But of course, this point is x plus delta x, has coordinate x plus delta x. This has coordinate x. Delta x goes in this direction. Just because of the way I chose to draw this thing, delta x is negative, but that doesn't matter. We just write down the run, which is going to be x minus x plus delta x. And then when we simplify the denominator, we get negative delta x. Now we don't want a negative delta x there, we want a delta x, so we multiply both numerator and denominator by negative 1, and we get this expression, f of x plus delta xy minus f of xy over delta x. And that's totally analogous to the expression we got for the slope in the y direction. So we have this expression for the slope and this expression for the slope. This expression for the slope on this face, this expression for the slope on the purple face. Now that slope represents the rise divided by the run. If we take the limiting value of that slope, this slope, as delta y goes to 0, we approach the instantaneous slope of a slice of the graph of the f of xy function. What we've got here is a slice of the graph. The green polytope is a slice of the graph. If we let delta y get smaller and smaller, and if this polytope approximates a function that curves as you slice it in the y direction, and curves this way as you slice it in the x direction, it should be clear that if we do smaller and smaller polytopes, that we're going to approach the slope of this curve in the y direction. Okay? And that's the rate of change. When x is held constant, you get a rate of change with respect to y. So, make the statement, that this is the instantaneous slope of a slice of the graph of f of xy, or the instantaneous rate of change of f of xy with respect to y, if x is held constant. Now, I was trying to drag out the term that's associated with that instantaneous rate of change of f with respect to y. And I asked for just one word. Well, half the class got it, the word derivative. This should remind you of the derivative, and it's just a one-dimensional derivative if you confine x to one value. Okay, over here, same thing, except now you're looking at the purple slice, which I've kind of abstracted here. Yeah, maybe there's a curvature here, and this slope, the slope of this this face of the polytope at xy is only an approximation to the actual slope, which is here. Well, to get the slope, a more accurate slope, you could do a polytope here, and the slope would be this. And then you do a polytope here, and the slope gets steeper, and these slopes approach this slope much in exactly the same way as slopes approach their limits in first-year calculus. So we've just reduced the two-dimensional function to questions about one-dimensional. We've taken the function of two variables and reduced it by holding y constant to the function of one variable, and then we just apply the definition. And we get, again, this limit is a derivative of f with respect to x. Now, we did an example of calculating these derivatives. We use partial of f with respect to x for the derivative that we get over here. It'll be this limit. And we're going to actually calculate that limit. That limit turns out to be just what we get if we have this function, x squared y. If we hold y constant, take the derivative with respect to x. And clearly, derivative of x squared is 2x. If you treat y as a constant, once it's a constant multiple, there we have it. And fy, you treat x as a constant, take the derivative of the square root of y. Okay, and x is a constant, it just goes along for the ride, and you get 1 over 2 square root of y. We can even do a second partial, and the second partial, we can do second partial with respect to x or the second partial with respect to y. Should be obvious, that's easy, at least once you get used to this idea. We could also do a mixed partial where we do f sub xy. Now, f sub x is going to stand for the partial with respect to x, f sub y for the partial with respect to y. F xy is going to be the partial with respect to x, y derivative thereof, the y derivative of the partial with respect to x. We also write that as second partial f with respect to x with respect to y. It's the partial of x with respect to f with respect to y, of the partial of f with respect to y. Partial f with respect to y is this, and then that's going to be partial with respect to x of x squared times that partial. It's going to be the partial with respect to x of the partial with respect to y, which is this, partial with respect to x of this. It's going to be this, it's going to be this. Okay, so calculation is very straightforward. Now, just a little bit more to talk about, and then I'm going to work out a partial derivative using the limits. We're going to work out the partial derivatives of this function using the limit definitions.